Okay, in section 3, we're going to look at a new kind of feature of our graph, one that we've seen a little bit before in our reciprocal function. That is what is called a vertical asymptote. So a vertical asymptote is going to be a vertical line, and we'll just say all vertical lines are of the form x equal a, that the graph approaches, but it does not touch or cross. So if I want to draw a picture of one, let's draw a graph. And let's just make a vertical line. And now this vertical line we typically make dashed because it's not actually part of the graph, it's just a feature where the graph approaches. And so now as the graph gets close to it, maybe it's flat here and then it gets close, but as it gets close, it typically will bend in one of two directions, either up or down. So this one bends up. And then from the other side, if it's going around flat, maybe this one bends down. So it gets infinitely close to this line, gets closer and closer and closer, but it never actually touches. So you can see in the couple pictures down here that these actually have vertical asymptotes. So if I look on this graph, you can see that there seems to be gaps in the graph where it seems that the graph tends to these asymptotes. So on this one, you can kind of almost envision a asymptote here and here. So this one appears to have vertical asymptotes at -2 and -1. This one over here appears to have one at 2 and only 2. So this one would have an asymptote of x equal 2. Very important that you always write x equal 2 or x equal whatever, because all vertical lines, remember, are in the form of x equal. Now the graphs are pretty easy to see these things, but we a lot of times also want to see algebraically how to find these. And we have a really easy method to do so. So if you want to find where a vertical asymptote is, they always appear in the same spot. So vertical asymptotes always appear when the denominator is 0 when in lowest terms, and that's the important part. Because remember, we're going to cross out any common factors, which are going to make our wholes, and then anything left, anything that makes it 0, is going to be a vertical asymptote. So if we look at this first function we have, this first example, it says 4x over x squared minus 25. So if I'm looking for the vertical asymptotes, of course, we'll still factor first. So I'll factor the denominator. So we have 4x, and then we have x minus 5 and x plus 5. So I know the domain in this case is all real numbers, except for 5 and -5. But it is already in lowest terms. So right away, since it's in lowest terms, anything that makes these things in the denominator 0 will be vertical asymptotes. So we'll have a vertical asymptote at 5, and we'll have a vertical asymptote at -5. Now here you can see I graphed it, and hopefully we can see that these asymptotes appear at the same spots. So I said at -5, which is there, and 1 at 5, which agrees with our algebra. So you can see these breaks in the graph for these vertical asymptotes at those two spots. Okay, let's look at this one. Now this one's a little trickier to write in factored form because there is no perfect square for 5. But as we remember from section 2, if we take x squared minus 5 and solve it, x squared is 5. So x is equal to plus minus square root of 5. So you can have asymptotes at irrational numbers. That is no problem. So we have x plus 6, and this would factor as x minus root 5 and x plus root 5. Now there is nothing that cancels out, obviously, so this is already in lowest terms. So both of these values would be vertical asymptotes. you'd have a vertical asymptote at x equals square root of 5, and you'd have a vertical asymptote at x equal negative square root of 5. Now, to check on the graph, we have to know what these are. These are about 2.23 and negative 2.23. So when we look on our graph, hopefully we see somewhere where around 2 and negative 2 we have asymptotes. So around negative 2.23, pardon me. So somewhere in that area, and that appears where there's an asymptote. And same thing here. Okay, let's look at this last one. So it says z of x is 4x minus 8 over x squared minus 8x plus 12. So I will factor both of these. So this one I can just take a 4 out of, 4 and x minus 2. And the bottom, this is a pretty simple factorization. Two numbers that multiply to 12, add to negative 8, minus 6 minus 2. And so now in this case, though, to put it in lowest terms, you notice that we cross out a 2. So, or an x minus 2. So there's going to be a hole at x equal 2. And we can figure out what that hole is here in just a second. So in lowest terms, this is 4 over x minus 6. So if I want to find the y value of the hole, I could plug this 2 into lowest terms. So it's 4 over negative 4, which is negative 1. And then there's the vertical asymptote. It's what's going to be 0 when it's in lowest terms. So we just have x minus 6 left. So if x equals 6 is a vertical asymptote. So on this graph, which I have graphed below in Desmos, I should see a hole at 2, negative 1 and a vertical asymptote at 6. Now obviously I see the asymptote at 6. That's really easy to see. You can see where it's broken apart here. Kind of makes sense. Now 2, negative 1 is the point here. It doesn't look like a hole is there. So we just got to make sure we draw it in there because the computer does not recognize that hole. It's there, but it's so minusculely small, the pixels don't actually show it on your screen. So let's look at a couple other examples where we're just trying to find the domain restrictions and figure out if they're asymptotes or holes. So again, asymptotes if they are in lowest terms and holes if they cancel out. So all these, we just want to make sure we're canceling once we factor. So this one, the easier part is to factor the bottom, x minus 1, x plus 1. And I encourage you to pause this, practice factoring these on your own because that's really the trickiest part about these sections. So this will be 3x and x, and this should factor as plus 1 minus 1. And if I wanted to check that, I could FOIL it out to make sure I do have the correct factorization, plus 3 minus 1, which gives us 2 in the middle. So this crosses out. So in lowest terms, we have 3x minus 1 and x minus 1. So the whole is going to be at x equal to negative 1. And again, if I want the y value for that, I can just plug that in up here. 3 times negative 1 minus 1 over negative 1 minus 1, which is negative 2 on the bottom, negative 4 on the top. So that would be positive 2. So that point is not on the graph, but it's essentially where the graph would approach. And this would have a vertical asymptote at whatever in lowest terms makes it 0, and that would just be x equal 1. So we have two domain restrictions because holes and vertical asymptotes are both restrictions on the domain, but one is going to make a hole and one is going to make an asymptote. Let's look at this second one down here, a little trickier factorization. So the denominator, the first thing I see is I see there is an x. So I would take the x out, just factoring that out. So that'll make it 3x squared minus 2, and I'm sure we can factor that more as we go. Now the top is actually difference of squares, a little different difference of squares, because 9x squared is 3x times 3x, and 4 is 2 times 2. So I can write this as 3x plus 2, 3x minus 2, using that same difference of squares procedure we've used a couple times. So now we just have to factor that trinomial in the bottom, and we will be good to go to start putting in lowest terms and everything. So I know it's got to be 3x and x, and it has to multiply to negative 2, but FOIL to negative 1, so I believe that's minus 1 and plus 2. because then there's your minus 3 and there's your plus 2. So when you FOIL, you get that negative 1 in the middle. Again, practice that factorization. So in this case, I see that this cancels out. So we'll have a whole at whatever makes 3x plus 2 equal to 0, and that would be x equal to negative 2/3. And we'd have a vertical asymptote. We actually have 2 of them, because don't forget about this little guy x. So there's going to be a vertical asymptote at 0, because you just have x, so that would be 0, and 1 at 1 as well for this factor. So there are 3 domain restrictions because there were 3 factors in the denominator. Only one turned out to be the whole, the other 2 were asymptotes. For this last example, we're going to try to build a rational function that has a couple things with it. So it says I want to build a rational function with a vertical asymptote of 1 and 2 and a whole at negative 3 and 4. So when I start this, the vertical asymptotes are the easiest because I know they have to have factors on the bottom that make them 0. So there's a good start. Now, I need a whole at negative 3 and 4. So I know I have to have a factor that cancels out to be negative 3. Now the problem is, this is fine, but I'm not sure it's actually going to go through 4. I know it has a whole at negative 3, but I doubt it's going to be at negative 3, 4. So if we think about in lowest terms, because essentially we're going to try to find some number a to multiply up here, because I can multiply any number to this function and hopefully get it to change the y value for this whole. So in lowest terms, this function I have so far is going to be a over x minus 1 over x minus 2. But I'm saying in lowest terms, if I plug in negative 3, so we're going to plug that in and hopefully get negative 4, or positive 4, pardon me. So if I put a 4 for my value, and I plug in negative 3 for my x, we'll try to figure out what a will give us that value. So we have 4, which is the y value of the whole, over negative 4 times negative 5, which is 20. So we have 4 equals a over 20. So if I multiply both sides by 20, I get an a of 80. So a really big a value. Well, the whole purpose of getting this now is I now know that my function that's going to give me those 2 asymptotes in that whole with that specific y value is going to be 80 times x plus 3 over x minus 1, x minus 2, x plus 3. And you can certainly FOIL this out to get it in a different form if you'd like. So graph this, check it, make sure our math is correct, and let me know if you do have any questions.